Assalamualaikum warahmatullahi wabarakatuh. I am Abdul Hamizi bin Abdullah. Today I will introduce about our projects. So our case study is about the capacity of existing road in a which was insufficient and the traffic was disturbed. So the new road along 3.5 km is constructed on soft soil. So Figure 1.1 show the new bypass road. The length of the road is 3.5 km. Each lane have one direction, so with the extra lane at junction, so the design traffic volume is about 19,000 per day in 2025. The second figure is show the subsoil, the soil structure. So the subsoil is extremely soft and compressible. The subsoil consists of 8 meter soft and compressible peat and organic clay deposit. So the groundwater table is high as 0.2 to 0.5 meter below the ground surface. So our group have preferred pile embankment construct on the soft soil for the road construction.
So for literature review, soft soil is defined as clay or silty clay soil which is geologically young. Soft soil is also defined as normal consolidated or under-consolidated or light over-consolidated fine-grained soils with very soft consistency. The properties of soft soil is that it has high water content, large void ratio, high compressibility, low shear strength and permeability, and it is non-homogeneous and its properties are highly variable and complex. Looking into this summary table right here, for example, from 1 meter depth to 1.8 meter depth, the basic soil type is peat soil. It has dark brown color and it's very soft clay with organic material with some of decayed wood and roots. And the qualifying terms is fibrous. On to the next slide. Problems related to soft soil construction is normally access problems, excessive settlement, embankment stability, and bearing stability. Therefore, to overcome these problems, pile embankment is used as the soft soil improvement. Pile embankment consists of a foundation on piles with on top of that an embankment. It is finished with a road. The materials used to build embankments or fields are often soil, although they can also contain aggregate, rock, or crushed pavement material. It is made of relatively high quality, well-compacted subgrade material that can hold the overlaying pavement layers and apply wheel loads without deflection or undesired movement. The material is laid out in thin layers ranging from 150 mm to 200 mm. In other words, 6 inches to 8 inches. Therefore, looking into this picture, this is the typical pile embankment design.
Hi, Assalamualaikum. My name is Muhammad Yusbi bin Sulaiman. Today I will present the proposed model. The process of designing begins with finding articles related to the pile embankment. The article must have the necessary parameters to be included in the software Plexis 2D. The parameters included are water content, coefficient of secondary compression, consolidation, and others. Pile embankment design is indispensable to determine the height, width, and size of the pile that are used in the article as shown in the figure. Second is the principle of pile embankment load distribution. Depending on the part of the emblem being investigated, the mechanism of load distribution varies. It is necessary to distinguish between load distribution at the embankment slope part and load distribution inside the embankment. Load distribution inside the embankment is based merely on the edge effect, while the slope parts of the embankment there is sliding due to lateral movement of the slope slide. Third is the designing model. Prior to the design, the soil features were recorded based on the article used to design this pile embankment. Table show the parameters for the characteristics of the soil in the area of the site. All these parameters will be included in the Plexis 2D software for analysis result from the software. Apply embankment constructed by the subsequent installation of piles, pile caps, and a reinforced embankment. The geosynthetic reinforcement is placed at the embankment base, which is a basal reinforcement. In this case, the embankment consists of recycled, crushed demolition waste aggregate, mainly concrete with friction angle 35. This material also acts as granular road base. The embankment was supported with concrete circular pile, and the size is 0.3 meter as shown in table. Distant piles for longitudinal and transverse are 2 meter respectively. Along the 60-meter stretch of the road construction site, the majority of the land is peat and organic clay. 10 piles are used to support 10 m wide of the road surface with an embankment height of 1 meter as mentioned in the figure. Thank you.
Hello and Assalamualaikum warahmatullahi wabarakatuh. My name is Fatin Parawani. So right now I'm going to present to you on step on how to model a pile embankment by using a Plexis 2D. So first of all, we need to enter our project information at this project properties tab, and then we click model and put all of the information, the model, the elements, and the most important part is our contouring values. And next we check the constant. If everything is okay, then click OK. So after it's all done, we need to create the borehole. So in Start tab, we can click this create borehole and choose one point. So after creating this point, for example, okay, we can click add, and then we need to put our value for our soil layer. So in this case, we put -8. So and also we can add the location of our water table. So the location of water table will be right up here, and then we can click OK. After we add the soil layer, then we can add the soil material. So we can add the material in this dialog box. So after we add these two, we can click OK. Then we can move to the structure step. So for structure, we need to add the fill embankment and also the pile. So to create the fill embankment, we can create this create soil polygon and choose the coordinate for each coordinate for the embankment. And then for the pile, we can create this. We can click this and create the create embedded beam row and choose each point on where we want to add the piles. So after we add all the piles, we need to create the interface. This is because we need to make sure that the pile and the soil surrounding it will connect to each other. So we can create the interface by click this create interface and put what we desired interface point. So after we we add the fill, the pile, and the interface, then we can move to mesh. So in mesh tab, we can generate mesh, and then after we generate mesh, for example this medium, then click OK. So I want to save time, so I just done. So after we view the mesh, generate mesh, we can view the mesh. So if we view the mesh, we can click this and the mesh will pop up. So after that, we need to move to another tab, which is the flow condition. So in this stage, so right here we already see our location of water table. Then if okay, then we can proceed to the stage construction. So in this in this tab, so first of all, we need to create the boundary condition for this model. By to add the boundary condition, we can click the model condition here and click up on the deformation, and then set the boundary condition for the deformation. And also we need to create the boundary condition for the groundwater flow. So as here, so the next step is to create the initial phase. So up here we have this initial phase. So by entering all the information here, then we can click OK, and then we add another 2, 3, 4, phase 1, phase 2 and phase 3 for our phase. So after we already add all the phase that we need, so we can select point for curve by using this. Okay, I haven't generated this, so we can create the point. So this is for us to analyze the point for each deformation and for water pressure. So we need to click for example 6 point, 3 for deformation and another 3 for pore water pressure. So after we selected the point, so we can calculate, and after we calculate we can view our calculation result. And by doing that, after all is generated, and we can see our result will be like this. Okay, and this one is for the pore water pressure and this one is for the settlement. So after all of this were done, so that means this is with piles. So we need to compare with the without piles one. So in this pile activation phase, we can deactivate this pile. For all pile, we can deactivate all of this. After we deactivate all of this, then the fill and the consolidation as usual. Then we click calculate again, and then view result calculation, and the result will be looking like this. So that's all from me. Thank you.
Okay, so for the result is in this design there are two materials set which were at the top was embankment and at the bottom was the pit soil. So there was another one material under the pit soil, which is sand. Why sand are not included in this design? Because sand has not been proposed to design because they will not give effect to the design. So based on the picture below that have a dot of red, so the node this is a node selected, which is the node A, B, C is a settlement node, which is the between embankment and also the pit soil, while for node D, E, F is access for pressure, which is in the pit soil. Okay, so for the settlement without pile, so based on the graph below, the graph was time again settlement. So they are not have the settlement, since the graph remainly constant at 0 from day 0 to day 112. So it will take a long period for the settlement to take place. While for the settlement with pi, from the graph from the picture, we can see that node C have less settlement occur because it is at the tip of the embankment, or at the end of the embankment. So the range settlement are between 0.03 meter until 0.04 meter, and it just take 7 days for the settlement to take place. So let's go to the excess pore pressure, which is without pile. So from the graph, we can see that node D have the highest excess pore pressure compared to the node E and also the node F. Why the node F have the lowest excess pore pressure compared to others? Because the selected node F nearest to the sand, while node D is far from the sand. So the maximum value of the excess pore pressure is at node D, which is the value is 11 kN per meter square. So the value of the F is lowest because the increment of stress due to the field construction decrease compared to the node D, which have more increment of stress due to the field construction. So from the graph that show the construction phase until day 7, so that the excess pore pressure increase at the maximum, there are lows for consolidation take place. Then the excess pore pressure dissipate or decrease, and it will take about 105 days
to reach the end of the consolidation. While for the excess pore pressure with the pile, so from the graph we can see that node D shows the highest pore pressure compared to the node E and also the node F. So the maximum value of node D is 4.418 kilonewton per meter square at day 7. So all the maximum value of node are at day 7. Day 1 to day 7 is the construction phase. After that, the consolidation takes place at the day 7 until day 7 plus, and it just take about 0.064 days to reach the end of the consolidation. So with the pile, it's only need 7 days for excess pore pressure and end of the consolidation compared with the without pile, which is it needs on 112 days.
For conclusion, our group decides to apply reinforced pine embankment for the entire bypass road based on the condition of the soil, which is soft and compressible. So based on the case study that we have proceed for this project, we have identified and compared the value of settlements and excess pore pressure distributions between the proposed model by using places and with unimproved soil from the journal. So more construction of road is expected to use a pile embankment for soft and compressive soil. So for recommendations, the author recommends adapting the quantification geotechnical risk in terms of whole life cost and life cycle analysis as a routine practice of assessment for selecting the best construction method. So therefore the risk assessment was decided in selecting the pile embankment as the preferred solutions